Hello and welcome in this video channel with me, Agatha Konstantia. Plant-based material such as fruit, vegetable, herbs or spices are generally now have been part of our daily meals. Plant-based food materials also possesses what is so-called as polyphenol compounds. In nature, these polyphenol compounds are naturally occur as a part of the plant defense system against any pathogenic bacteria, fungal, or also virus attack that may harm the plant cell. That is the reason why these polyphenol compounds also naturally have such as antibacterial activity, antimicrobial, antifungal, and as well antiviral activity. Now, we can also remember and see from our daily fruit and vegetable that polyphenol compounds also may giving rise of coloration in certain fruits and vegetables. Take an example, the red color that we can find in red onion, or also the red color that we can find in red cabbage. Yes, the red color in such fruits or vegetables can be explained by the content of anthocyanin. Anthocyanin is a phenolic compound that belongs to the group of flavonoid, and it also possesses such antioxidant activity. Now, what is deemed to be beneficial for our human health within our human daily meals is that these polyphenol compounds possesses such antioxidant activity. Antioxidant substances is beneficial because it can stabilize or neutralize the free radicals that naturally occur in our body. Now we remember that these free radicals is generally undesirable to be presented in our body. Why? Because free radicals are substances that are highly reactive and unstable, so that it is highly reactive and can react easily with any other molecule in our body and thus can cause such as a damage in our cell and also may rise to the oxidative stress that is undesirable for our health. That is the reason why we need a presence of antioxidant substances that can help in neutralizing or stabilizing this free radical. However, it needs to be bear in mind that this free radical is also naturally occurring in our body because free radicals itself is actually a product of a normal cell metabolism such as respiration. It means that when the cells are using oxygen, thus the free radicals compound are also produced in our body system. Now, what is that rising concern that is undesirable is a condition or situation in which there is an imbalance between the production of free radicals and insufficient amount of antioxidant substance. In this kind of circumstances, then the free radicals will may raise concern because it then can lead to cause such an oxidative stress and eventually may lead to a kind of diseases. That is the reason why we also need the help to eat such fruits or vegetable or any foods in our daily meals that also possesses antioxidant substances and particularly that possesses the antioxidant activity. So that this antioxidant activity can help in stabilizing or neutralizing the free radicals and hence contributing to strengthening our immune body system. Now in this video, we are curious to see the types of phenolic compounds that is present in our surrounding, especially what is present in our daily fruits and vegetables, for example. And as well, we will be also delving into seeing how the structure of these polyphenol compounds may contribute to the antioxidant activity. polyphenol is a large group of substance that has a naturally occurring phenol structure. Now, I think it would be beneficial for us to refresh a bit of our mind of the structure of phenols. Phenol is a structure that consists of a benzene ring with one hydroxyl group or OH group that is attached to the benzene ring. Now we will refresh our mind a bit of the structure of phenol. Let's start with the structure of the benzene ring. Benzene, or also known as the C6H6, consists of a structure that have a planar hexagonal, meaning that it has 6 carbon atoms in a cyclic condition. Cyclic meaning that it makes the closed cyclic ring. And now, what is really special of this benzene ring is particularly that it has an alternating double bonds. The alternating double bonds meaning that here we have double bond, and in here we don't have any double bond. Then we have again our double bond. Here we don't have any double bond, and here we will have double bond again. So this is the structure of benzene ring. We can also draw the structure in another form, such as just depicting a planar hexagonal which explaining the hydrocarbon cyclic ring, but then the alternating double bonds is then just simplified as the circle in the middle of the benzene ring. It is the simplified version that we can also draw in order to referring to the benzene ring structure. Or in the real structure, we can also draw the benzene ring structure as depicting with the cyclic hydrocarbon ring, meaning that, of course, we need first to draw the alternating double bonds. So remember that the carbon atom always only have four interaction with any other carbon atom. We have here the double bond, and we don't have here. We have here, we don't have, and we have here. And now, of course, it also represents any hydrogen bonds that is connected or linked to the carbon atom for sure, because as such it is called as the hydrocarbon, meaning that it just consists of CH chains. It's a carbon and hydrogen, or carbon and hydrogen structure. And of course, then we can start to count 1, 2, 3. So it has H for sure. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. And ultimately, every carbon atom in this benzene ring, of course, represents the CH. So this is 3 ways that we can depicting the drawing of the benzene ring of interest. Now, the thing that we are interested is the structure of phenols for sure, because we are discussing about polyphenol compounds. It's very easy. If you have already understand and remember the structure of the benzene ring, then polyphenol or phenol is a structure that having the benzene ring. I will just draw the simplified version that we understand this is the benzene ring, and particularly it have one hydroxyl groups or OH group, so called as hydroxyl group. It is attached to one of the carbon atom that belongs to this benzene ring. And here it is, we already have the structure of phenol. polyphenols comprises a lot of group of substances which have a naturally occurring phenol structure, as what we have just discussed before previously. And now, these polyphenols just can be categorized into 5 main groups, namely flavonoid, phenolic acids, stilbens, tannin, and also lignan. You might probably have already been familiarized in hearing some of the names of these polyphenol compounds. And as we know, even though all of these polyphenol compounds, for sure of things, must contain the structure of phenol structure, however, each group of these main groups are diverse in a unique structure from one another. And later on, each of the group also can be categorized further into another subgroup. As what we can find here, for example, flavonoids then can be categorized into another 6 subgroup, namely flavones, flavonols, flavonols, isoflavone, and anthocyanidin. You might also have probably familiarized with the name of the compound that we have here, such as quercetin, for example. Quercetin is a compound that belongs to the flavanols group of the flavonoid that we can find in the red onion, for example. And talking about phenolic acids, Phenolic acids is the simplest structure compared to another groups of any other polyphenols. In phenolic acids, it can be categorized further as the hydrobenzoic acids, or often be simplified, called as HPA, hydrobenzoic acid. So, in brief, this kind of compound is a derivative of benzoic acid. Later on, we will be delving into that discussion as well. Or another compound that belongs to the phenolic acid is, for example, caffeic acid, that it is very familiar in our ear, I think. We can often hear the name of caffeic acid in coffee, for example. And the phenolic acid that belongs to the hydrobenzoic acid, for example, gallic acid or phenolic acid, that is also responsible for the aroma of vanilla. And then the stilbens, we have here the stilbens derivative, for example, the resveratrol. I think you might also have heard several times about this compound that mainly be found in the grapefruit. And rest, we have tannin that can be categorized as hydrolyzable tannin, such as tannic acid, that is very famous in giving the astringent sensation in several fruits or vegetables. And the other group is the non-hydrolyzable tannin, such as procyanidin B2. And the last here we have the lignan. So these all are the compounds and the main group and the subgroup of the polyphenols. However, we are not going to delve into each of the structure. This time we will particularly interested in discussing example of the simplest structure of these polyphenols in order to understand how this structure of polyphenols can explain the antioxidant activity. Phenolic acid structure can typically be identified by the structure that consisting of a phenolic ring and another structure of carboxyl group that will explain the carboxylic acid function. Now we will try first the phenolic ring. The phenolic ring, remember the structure of benzene ring with the one hydroxyl carbon that is attached to the benzene ring? We will draw this structure first. So here, obviously, we have a benzene ring. And then in this benzene ring, if there is a hydroxyl group that is attached to this benzene ring, then here we obviously already have the phenol structure. Now, as we are actually interested in the structure of a phenolic acid, of course, then it is obvious to know, or at least to be able to identify, what is the structure of the acid of interest. So that here, the structure of phenol that we have already obtained, of course, we need another structure that can explain the acid of the structure. So here, we need another structure, which is a carboxyl group. By having the structure of carboxyl group, it explains the carboxylic acid function of the phenolic acid. So here, obviously, we already have the structure of the phenolic acid. Consists of, or at least we can say that we can identify by a structure that having a benzene ring and one or more than one hydroxyl groups that is attached to the benzene ring, which is then can be called as the phenolic ring. And of course, obviously, another structure of COOH, or also as known as a carboxyl group. Which explain the function of the carboxylic acid. So here is the general structure of the phenolic acid. Now that we have been able to identify a structure of phenolic acid, and in this case is the general structure of phenolic acid, we will now try to see the example of the simplest structure of the phenolic acid, which is the gallic acid. Gallic acid is one of the example compound that is categorized as the phenolic acid. Now, we need to bear in mind that gallic acid is the derivative of the benzoic acid. Now, this gallic acid already possesses a phenolic compound because it is categorized as the phenolic acid. However, the benzoic acid itself is naturally or initially is not a compound that belongs to a phenolic acid. Here, we will try to draw the structure to be able to understand it in more easier. Now, what I'm going to try first is the structure of the benzoic acid, which is a non-phenolic compound. Obviously, the benzoic acid, of course, consists of a benzene ring, and as it is called as a benzoic acid, meaning that it also needs to have a structure of a carboxyl group that explains the carboxylic acid function. And here we have the C, double bond O, and single bond to O and hydrogen. So it is the structure of a non-phenolic compound of benzoic acid. Now, obviously, the mechanism of how this benzoic acid then can turn into a gallic acid, which is a phenolic acid compound, is because of the addition of one or more than one hydroxyl groups that is attached to the benzene ring. by the addition of one, for example, hydroxyl group that is attached to the benzene ring of the benzoic acid, then we here already have the structure of the hydroxybenzoic acids, or also can be called as HPAS. So it's a broad range or groups of compounds that is a derivation of the benzoic acid because of the addition of the hydroxyl groups to the benzene ring itself. However, to be able to obtain the structure of the gallic acid of interest, then the addition is not only one hydroxyl but also need three hydroxyl groups to be attached on the benzene ring. So here we have another hydroxyl groups that needs to be attached in this benzene ring. And after that, here we have already the structure of the gallic acid. Now, as it is obviously can be seen that it already consists of three hydroxyl group, thus the gallic acid can also be called as a 3-hydroxy benzoic acid. Now, in phenolic acid structure, as have been depicted by our example of gallic acid, the antioxidant activity is strictly decided by the number and the positioning of the hydroxyl groups that is attached to the benzene ring of the phenolic acid. And study has also revealed that the strength of the antioxidant activity of such structure of the phenolic compound following as follows. Monohydroxy has less strength antioxidant activity compared to dihydroxy and trihydroxy. It means that if we take a look again in our structure of gallic acid, it obviously has three hydroxyl groups that is attached to the benzene ring. Thus, it can also be called as a 3-hydroxybenzoic acid. Therefore, from here, from the structure, we know obviously that gallic acid possesses quite high antioxidant activity as it is categorized as a 3-hydroxy or having a 3-hydroxyl groups that is attached to the benzene ring. Now, in addition, studies has also revealed that the structure of carboxyl group that explain the function of the carboxylic acid in a phenolic acid, which is here, the carboxyl group or the C double bond O and attached to the OH or COOH. The COOH structure or carboxyl group is not directly explaining the antioxidant activity of the phenolic acid. However, the structure of C, double bond C, and COOH, so it is the whole structure from here, C double bond C, as well as include the carboxyl group. It does have an important role in stabilizing the free radical via resonance. It will be clearer more if we can draw the mechanism of how such structure can be able to stabilize the free radical via resonance, but for now, we will discuss that in another occasion. Now that we have been discussed quite a lot about the phenolic acid as a compound that belongs to one of the group of the polyphenols. Now I think it is going to be a good time for us to refresh our mind a bit of our understanding and memory about the free radicals. So, free radicals is a product that is produced by a normal cell metabolism inside our body. It means that when cells are using oxygen in certain metabolism pathways, for example during respiration, a free radicals which is then will be produced. And normally there are two types of the free radicals that is widely known. The first one is the ROS, or the reactive oxygen species, which is mainly produced, for example, during the respiration metabolism. And another type is the RNS, or reactive nitrogen species, which is mostly found in the blood vessel. Now that this free radical can be defined as molecular entities which have an unpaired electron in the outer atomic orbital. So most of the time, the unpaired electron is denoted as a dot that is being placed near to the atomic that have the unpaired electron. For example, if we here has the case of the ROS, or the reactive oxygen species, meaning that there is an oxygen atom that have an unpaired electron in its outer atomic orbital, then we will denote the free radical or the unpaired electron near the oxygen atom. So it will be denoted as OH free radical. Or another example is the superoxide radicals, which is denoted as the O2 radical minus. And if we remember it, the initial structure before it becomes a radical, or let's say the initial structure when the oxygen atom has a paired electron, thus it's not radical yet, is for example, let's take into account a peroxyl radical, which is denoted as the ROO free radical. We can compare that before it loses the one of the electron and then it become unpaired electron and become radical. For example, it can be denoted as the ROOH. But because of the redox reaction, or the reduction and oxidation reaction that is occurring during the metabolism inside our body, for example during respiration, the redox reaction thus can cause the oxygen atom to lose one of the electron, thus its electron in the outer atomic orbital become unpaired. And this unpaired condition, the unpaired electron condition, can cause the properties of the free radicals, which is highly unstable and also highly reactive, meaning that free radicals is easily react to another molecules or individual electron or atom of another molecule in order to be able to stabilize themselves. Now, this mechanism may also lead to so-called as a chain reaction, meaning that it is a sequence of reaction in which the reactive product or the byproduct of the reaction is coming to a sequence of reaction. And so on until the mechanism finally terminated, when eventually this free radical is stabilized and ultimately reaching its stable form. Now that we have been previously discussed about the structure of gallic acid, now let us take a look into the structure and how the mechanism of the structure of gallic acid may be able to stabilize free radicals. Here we have our structure of gallic acid, which is depicted the structure of phenolic acid. And remember, as you can remember, that our gallic acid is particularly have a specific structure, which is the 3 hydroxyl groups that is attached to the benzene ring. Now let's assume that our gallic acid is in interaction with a free radical. Now we already can remember that the number and the position of the hydroxyl groups is what defined the strength of the antioxidant activity of a phenolic acid compound. Now that in this case we have the free radical, which is highly unstable and highly reactive. This free radical has unpaired electron that really easily react with another molecule, and in this case this free radical is interested to react with the structure of our gallic acid in order to stabilize itself via the redox reaction or reduction and oxidation reaction, in which comprising of the reaction of donating and accepting electron. Now that our free radical here really want to make itself stable by accepting or donating electron from the part of our gallic acid. The question is, which one of the part of the structure of our gallic acid that may be able to support in the stabilization of this free radical? The answer is, of course, on the on the hydroxyl groups, because this hydroxyl groups is what is directly exhibit the strength of the antioxidant properties of our gallic acid. So we have already know as a clue that this radical is interested to react with one of our hydroxyl groups here. But now the next question is arising. That we have 3 hydroxyl groups. Which one of the hydroxyl groups that will react with our free radicals? The answer eventually comes to the position of the hydroxyl groups that exhibit the low binding energy. And the low binding energy of our hydroxyl groups is located in the center one. That's why we can see here that our free radical is interested to react with the hydroxyl groups, which has the low binding energy of interest, which is in the center one, compared to another in total of 3 hydroxyl groups that we have. And so on the reaction is happening that the free radical exchange the electron, either donating or accepting the electron from our hydroxyl groups, and eventually, after the reaction happened, the redox reaction happened, our hydroxyl groups is finally can be stabilized. It's finally reaching the state of a stable form, an RH. The unpaired electron is now has been stabilized. But now the question is there anything changed with the structure of our gallic acid? Eventually, yes. It turns out that the redox reaction between our gallic acid and the free radical has already converted our gallic acid into another form, which is now the hydroxyl groups that has been reacted to the free radical is now become a radical itself. And because of this structure, it is also can be called as a phenoxyl radical. However, the good news is that this phenoxyl radical that we have in our gallic acid now is, however, still much more stable and less reactive or less unstable compared to the initial free radical. So it is kind of good news. But however, as it is still a radical, meaning that this phenoxyl radical is still unstable and of course naturally wants to stabilize itself. But the question now is how it is possible? How is it possible? How does the phenoxyl radical in our gallic acid can stabilize itself? Thankfully, we have the answer. We have to be thankful for the structure of the gallic acid that we have. Because now remember that we have another two hydroxyl groups in our gallic acid, and eventually it can become the answer of stabilizing the phenoxyl radical that we have in our gallic acid. It is called as a stabilization via two intramolecular bond. Here we see that the OH and OH, or the two other hydroxyl groups, may be able to stabilize the radical parts of our gallic acid via hydrogen bonds. Hydrogen bonds mean that there is a bond between hydrogen and this is oxygen atom that we have as a radical part of our gallic acid. And because this bond is happening within the same structure of the same gallic acid, thus we can also say that it happens as an intramolecular bond or intramolecular H bond of particular. In addition, it also can be called as orthohydroxyl group. Why? Because the other two hydroxyl groups is just located side by side by the present of our radical part in our gallic acid. Remember that if we have the structure of a benzene ring, if we have the structure of a benzene ring and have the position of 1, 2, then we will call it ortho. If we have the position of 1 and 3, it will call as meta. And if it occurs in the position of 1 and 4, it will call as para. Yeah, so remember the position of ortho, meta, para. Now, because of course that obviously the hydroxyl groups is located just side by side, it can be for sure just be called as an ortho position. Thus, it can be called as orthohydroxyl groups. So this is, in conclusion, a depiction of how the structure gallic acid, as one of the compound belongs to phenolic acid, may be able to stabilize the free radical via its structure and thus explaining its capacity as an antioxidant. We have now reaching our last part of our discussion today. It has been a very interesting discussion with you all that have been delving into some parts of understanding or seeing how the structure of polyphenol may be able to stabilize a free radical, thus explaining the capacity of its antioxidant properties. Now that in first we have already discussing a bit about the groups of polyphenols, quite a lot of group of compounds that can be categorized as polyphenols with each of different structure as well as a bit of different mechanism of how it can stabilize free radical. And then we have moved forward into understanding a bit about what antioxidant is and also about the free radical characteristic and how it may behave to go to a tendency to stabilize itself via reduction and oxidation reaction. And finally, at the last part, we have also been already delving into seeing how the structure of phenolic acid, which was depicted as gallic acid, and how the structure may be able to explain the antioxidant properties of it in stabilizing the free radical. Now that eventually we are about to come to conclude our discussion now, and to put a cherry on top of what we have discussed now, we already know by heart that the free radical is a product that is produced by the normal cell metabolism that is occurrently or naturally happening inside our body. And yes, it is true that free radicals is generally undesirable because it is very reactive, highly unstable, meaning that it can easily react with another molecule or cells inside our body. This can causes the oxidative stress and eventually may lead also to any kind of degenerative disease, such as, for example, diabetes type 2 or also another degenerative disease, which is undesirable for our health. But thankfully, the good news is that it also has been known for long, or at least since 1969, that naturally in our body itself, our body system also exhibit or produce the antioxidant enzyme, such as so-called as superoxide dismutase or SOD. Superoxide dismutase is a kind of antioxidant enzymes that for sure playing an important role in stabilizing the free radicals that naturally produce in our body system. And we have always remembered that as long as the amount of the free radicals and antioxidant is in balance, then everything is good. Then everything is good. But however, it will become a rising concern when it comes to the situation that our free radical that is produced in our body is much, much more higher in amount compared to the antioxidant that is produced in our body, thus leading to the imbalance condition. And this just a kind of condition that is undesirable that may lead to adverse effect on our health. And therefore, it is always helpful to eat and consume food that contain the antioxidant properties. So to conclude all of our discussion, it is very good. Don't forget to eat our meal, and this time don't forget to eat as well as the colorful meals, fruits and vegetables, which also may contain antioxidant activity that can be helpful in supporting our immune system and our body system as well. After all, thank you very much for our discussion and time. It is very nice to have a discussion and time with you. I hope it is also useful for us, and I cannot wait to see you on our next occasion. Bye bye!